Let's talk about the 6 trig identities and a few more we can derive from our unit circle. So we need to know there is sine of theta, there's cosine of theta, there's tangent theta, which is equal to sine theta over cosine theta. The cosecant of theta is equal to 1 over sine of theta. So the way I remember these is that the c goes with the s. And then secant of theta is 1 over cosine theta. So again, the s and the c go together, not the s with the s. And then cotangent of theta is equal to cosine of theta over sine of theta. So notice on this one I remember it because cotangent of theta has a c and cosine of theta has a c. So c does go with c here, but then cs, sc, c goes with c, and tangent starts with sine over cosine. But you have to remember these 6 trig identities because sometimes you need to simplify expressions with knowing that, for instance, cosecant is equal to 1 over the sine, but we're going to look at those in just a minute. Another very important identity is the Pythagorean identity. We get this from the unit circle. So here's a little tiny unit circle over here where I just wrote the basic equation of our unit circle, which is x squared plus y squared equals 1. Any point on that unit circle with an angle of theta, so it can be any angle, is going to have the coordinates cosine theta, sine of theta. Cosine is our x and sine is the y. So we could easily replace with the x squared plus y squared equals 1 equation, we can put in cosine squared theta plus sine squared theta equals 1. And that is where the Pythagorean identity comes from, straight from our unit circle. There are 2 more identities we get from the Pythagorean identity. Let me show you those 2. So from the Pythagorean identity, we can easily derive 2 more identities simply by dividing by cosine squared theta and dividing by sine squared theta. So I rewrote the Pythagorean identity right here at the top. Cosine squared theta plus sine squared theta equals 1. And then I divided everything by cosine squared theta and I reduced each term. So for the first part, cosine squared theta divided by itself is just equal to 1. For the second term, I have sine squared theta divided by cosine squared theta, which is equivalent to tangent squared theta. And then 1 divided by cosine squared theta is equivalent to secant squared theta. So this helps us to simplify expressions involving the secant, and we'll see that in just a second. Another one we can derive easily from the Pythagorean identity is this one. If you divide everything by sine squared theta, a similar result happens. Cosine squared theta divided by sine squared theta is equivalent to cotangent squared theta. Sine squared theta divided by itself is equal to 1. And then 1 divided by the sine squared theta is equal to the cosecant squared theta. So when we see cosecant squared theta, we, for instance, know that's equivalent to cotangent squared theta plus 1 if we need to replace it. So let's just look at a few examples of this. Now there are many variations of examples, but I just picked 4 to give you an idea of what you might see that you need to simplify with the trig identities. So these 2 examples are just to simplify the expression given. So number 1 gave us cosecant squared theta minus 1. So we would need to use the one up here that has cosecant involved, because cosecant squared theta minus this 1 would be equivalent to cotangent squared theta. So I can see right there, if I subtracted the 1, then that's equal to what's left, which is cotangent squared theta. So I'm going to replace it. So then I bring down tangent squared theta in my next step, and then I'm going to replace each one of those with what they are equivalent to. So like on the first board we looked at, the cotangent is equal to the cosine over the sine. If it's squared, it just means that the cosine and the sine are now squared. Let me bring that line over a little bit. Tangent squared theta is equal to the sine squared theta over cosine squared theta. And then we see what we can simplify. So your goal with these expressions is to try to get everything in terms of sine and cosine. That is what you're working on. So simplified means try to get it all in terms of sine and cosine and then see what happens from there. So we can see sine squared would cancel out because these are multiplying. and cosine squared would cancel out. So it's really ends up being equal to 1, not 0, because it ends up as cosine squared theta, sine squared theta divided by itself, which is equal to 1. So we're done with that one. Let's look at example 2. I just want to simplify this expression. I already have sine and cosine, but I need to help clean this up a little further. 1 minus sine squared theta comes from the Pythagorean identity that we looked at on the first board. So let me get a different color to write this over here on this side. We wrote down on our first board cosine squared theta plus sine squared theta is equal to 1. So 1 minus sine squared theta, in other words, if I subtract sine squared theta, I would end up with cosine squared theta is equal to, because these would cancel out, it's equal to 1 minus the sine squared theta. So that means I can replace 1 minus sine squared theta with cosine squared theta, because in math we're allowed to substitute when we know something is equivalent. So I'm going to replace this with cosine squared theta. It still has this cosine squared theta that it's being multiplied by. So using our exponent rules, we would put these together. I have 2 cosines and 2 more cosines, so I really have 4 all together. We add up those exponents. And so that's what this one would simplify to be, cosine to the 4th theta. All right, let's look at 2 more examples. What if you're asked to prove that this is true? We need to prove the tangent of y over the sine of y is equal to the secant of y. So using our trig identities, we are going to prove that this does happen. So we want to put things in terms of sine and cosine, like I mentioned just a minute ago. So the tangent of y is equivalent to the sine of y over the cosine of y. I'm going to leave an improper fraction here, like a compound fraction. The secant of y is equal to 1 over the cosine of y. We'll write that down. Now we need to clean this up. In math, we don't, let me write this a little bit darker. That was the sine of y. But in math, we don't like to divide a fraction by something. So instead we multiply by the reciprocal. So I'm going to rewrite this as sine of y over cosine of y times the reciprocal. So in the denominator, you have to remember this is your denominator. That's sine of y over 1. So I'm going to rewrite it as 1 over sine of y. We'll bring down what was on the right. So now these are multiplying. So sine of y and sine of y would cancel out. And then you can see that 1 over the cosine of y is equal to 1 over the cosine of y. So we have proved that those two were equivalent by putting things in terms of sine and cosine and then using rules that we've always known in math. Like when you multiply and you divide by something, they would cancel out. So let's look over here at number 2. I'm going to draw a little boundary line. So we have sine of y plus sine of y cotangent squared y equals cosecant y. Now again, you're aiming to get things in terms of sine and cosine and go from there. So we have sine of y, let's leave that alone, plus sine of y, I'm going to still leave that alone, times cotangent squared y. Let's put that one as cosine squared y over sine squared y equals, and then cosecant y is 1 over the sine of y. And now I can look for what I can reduce or combine. So let's see, we have the sine of y will cancel out one of the ones in our denominator. So I'm going to bring down the sine of y plus the cosine squared y over sine y, but it's no longer squared, equals 1 over the sine of y. Now these two are adding. I can't add without a common denominator, so I'm going to work on getting a common denominator. This one has a 1 right now. So to make this one have a sine of y, I need to multiply it by sine of y. And then what I multiplied the denominator by, I have to also multiply the numerator by. So now I would have sine squared y in the numerator divided by the sine of y plus cosine squared y divided by the sine of y equals 1 over the sine of y. Now in math, we have a rule about our denominators. If they all have the same exact denominator, we would be able to multiply everything by the sine of y and they all cancel out. So we can cancel them out when they are all identical. And we are left with the sine squared y plus cosine squared y equals 1, which we know that is true because that is the Pythagorean identity that we've already mentioned. So we have proved that that is true.